Hello everyone, my name is Jinming. I'm from Department of Electrical and Computer Engineering, University of Minnesota. I'm glad that I have a chance to present my work in this conference. The topic I would like to present is synthesis of alpha double prime and 1692 foils with an ultra-low temperature coefficient of coercivity for rare-earth-free magnets. This work has already been published, and you can download the full paper for more details. Here's the outline of my presentation. First, the introduction part. I will introduce rare-earth-free permanent magnets and the basic properties of alpha double prime and 1692, and tell you about why it's a promising candidate for rare-earth-free permanent magnets. Second part is the approaches to synthesize alpha double prime and 1692, and then it's alpha double prime and 1692 foils prepared by a low temperature nitriding method. So the last part is a summary of my presentation. Here are the applications of magnetic materials. In this slide we can see the various applications of magnetic materials, from canvas, permanent magnets, generator motors, and these memory devices or bio applications. So in this presentation, I will more focus on permanent magnets materials. First, I will talk about the development of permanent magnets. Several basic parameters will be introduced first. This is a schematic drawing of hysteresis loop of magnetic materials. Its M stands for magnetization and H for magnetic field. This is saturation magnetization, resonance, and coercivity. By using this equation, we can convert this MH loop to BH loop. B here is magnetic flux density. In the second quadrant of BH loop, you can get a maximum B times H, which is called the maximum energy product. S indicates the energy density of a specific magnetic material. And in this chart, we can see the development of permanent magnets in the past century, and the BH max increased significantly from steel to neodymium iron boron permanent magnets. And when new magnetic materials are developed, like samarium cobalt or neodymium iron boron, and the BH max increase significantly. So it's important to develop new magnetic materials for permanent magnets. And also in the insert, we can see with the same magnet energy, like when materials with small BH max like steel, you need a large volume to have the similar magnet energy. But for materials with high BH max like neodymium iron boron, you just need a tiny piece. So in this figure, we can see the high performance permanent magnets are all rare earth based, but there are some issues for rare earth elements. I'll talk in the following slides, and that's also why rare earth free permanent magnets are preferred. For rare earth elements, they have high prices, environmental issues, and supply limitations. These two are rare earth elements which are important composition for neodymium iron boron permanent magnets. We can see their prices are much higher than that of gold. Also, during the mining process of rare earth elements, lots of pollutions can be produced which are not good for our environment. Additionally, the supply of rare earth elements are mainly from China. There might be a potential supply limitation. So that's why more and more researchers are focused on rare earth free permanent magnets. So for these candidates, they should have the following criteria. First, they should compose of earth-abundant elements instead of using rare earth materials. Another one is that they should have high magnetic anisotropy and large saturation magnetization in order to have high pH max. Alpha double prime and 692 is a promising candidate for rare-free permanent magnets. First, both iron and nitrogen are earth-abundant elements. Also, this kind of material has high magnetic anisotropy and large saturation magnetization. And from this chart, we can see a large switching field of the alpha double prime iron 692 CPP GMR. So this large switching field is due to the high magnetic anisotropy of this material, which is estimated up to 1.9 times 10 to 7 erg per cubic centimeter. Also, the high saturation magnetization of alpha double prime and 692 has been observed on different kinds of samples, from thin films to powders and nanoparticles. The saturation magnetization we can see is reported ranging from 2.4 to 2.9 Tesla, which is even higher than that of iron coal alloy. So this material, alpha double prime and 692, has high magnetic anisotropy and large saturation magnetization, which is good for high pH max and large roughness. So that's why it's a very promising candidate for rare-earth-free permanent magnets. Here's an example of the high pH max of alpha double prime and 692. This sample is a thin foil sample. The thickness is around 500 nanometer, and nitrogen iron was introduced into the sample by iron implantation, and different dose has been used, and we can see the change of the coercivity of the sample. And the enhanced coercivity is due to the formation of alpha double prime and 692 phase, which can be confirmed by the X-ray diffraction pattern and the select error diffraction pattern of TEM images. So yeah, use this loop and we can calculate the energy product pH max can up to 20 MeV/Auster. So the next question is how to synthesize alpha double prime and 692. Based on the iron nitrogen phase diagram, there are generally two approaches to synthesize this material. One is the high temperature approach, and the other one is low temperature approach. For high temperature approach, iron as a precursor and doing the nitriding process higher than 600 degrees C, and you get gamma iron nitride, and then quenching down to get alpha prime iron nitrogen, in which nitrogen is not ordered, and do a low temperature tempering process. Temperature usually lower than 200 degrees C, and finally you can get alpha double prime and 692. The other methods is use iron or iron oxide as precursors to do the nitriding at temperature lower than 200 degrees C, and you can finally get alpha double prime and 692. The crystal structure of gamma iron nitride and alpha double prime and 692 are shown in this slide. This is the gamma iron nitride. Here's iron atoms. These are octahedral interstices. One nitrogen atom is randomly located at these interstices. When nitrogen introduced, and there is a distortion as shown in figure B here. So this is the schematic drawing of the crystal structure of alpha double prime and 692. This is a body-centered tetragonal structure. Since we will use a low temperature nitriding process to synthesize alpha double prime and 692, here I have a brief summary on this topic. These papers are published recently, and all the starting materials are nanoparticles. This is because nanoparticles are easy to be nitride due to the high surface to volume ratio, However, nanoparticles are difficult to handle and easy to be oxidized. Let's think about other format of samples can be handled by this low temperature nitriding process. So we use thick foils like 25 micrometer thick, which can be thousands times thicker than that of the diameter of nanoparticles. The foil samples are relatively easy to handle and good for mass production. But the challenging thing is like how to increase the nitriding efficiency for such a thick sample instead of the nanoparticle samples. The foil samples are much thicker than that of nanoparticles, so the microstructure needs to be tuned to let nitrogen easily diffuse through the sample to get high nitriding efficiency and high phase volume ratio of alpha double prime and cysteine. We proposed a oxidation and reduction process to introduce the porous structure. As we can see in this figure, after the oxidation, there's an inner layer and outer layer of the iron oxide. This is the original surface of the foils. So the volume expands. And then we can do the reduction process to get rid of the oxygen and then form the porous structure. Different porous structure can be formed based on different reduction parameters. After the combined oxidation and reduction process, porous structure can be introduced into the foil samples. And here I have a schematic drawing of how the microstructure changes in the foils. At the very beginning, the raw foil is a solid structure and also the grain is solid grain. And after the oxidation and reduction, you have a porous structure. And for the grains, there are some nano-sized channels introduced in. The channels are from some deformations or dislocations. And these channels can help the nitrogen diffuse into the foil and react with the grain much easier. So in this way, samples with high phase volume ratio of alpha double prime can be obtained. And also these nanochannels been observed on some nanoparticle samples have been reported. Experimental details of synthesizing alpha double prime and 16 nitrogen 2 foils is shown in this slide. We use a box furnace for the oxidation, which happened at 980 degrees C to quickly oxidize through the 25 micrometer thick iron foils. After the oxidation, the reduction has happened in a tube furnace using hydrogen gas. After reduction, the nitriding was happened in a similar tube furnace use ammonia gas. The nitrogen temperature is lower than 200 degrees C. Here's the steps and how the microstructure changes, and we can see after the oxidation and reduction we can obtain the porous structure of the foil samples, which are good for the low temperature nitriding process. This slide shows the low temperature nitriding on iron foils and how we use these foils to prepare a piece of magnet. So here are the steps of the foil samples. These are the pictures of these samples for the raw foil, oxidized foil, reduced foil, and nitride foil. For the nitride foil, and we can stack together to form a piece of magnet. X-ray diffraction patterns are collected on the foil samples at each stage. It's raw foil, oxidized foil, and reduced foil. So the phase information here from iron to iron oxide and iron again. During this process, a porous structure was introduced into a foil sample. which can help increase the nitriding efficiency greatly. This figure shows a typical nitride sample of foil samples. The main phase is alpha double prime and 692, denoted by black square. And also some over-nitride phase is observed, so you can minimize the over-nitride phase iron-3 nitrogen here by modifying the nitriding parameters. Both SEM and TEM are used to characterize the morphology of the nitrided foils. These are cross-section SEM, these are TEM. By zooming in the SEM image, we can see the porous structures in the foil. The porous structure might be more obvious in the TEM images, shown in these figures. The nitrogen can diffuse through the pores and react with iron grains to help enhance the phase warming ratio of alpha double prime and 16 nitrogen 2. The EDX data were also collected as shown in this figure. The red dot stands for nitrogen and blue for iron. Most of the grains are well nitride, but for some larger grains, still some unreached region left in the center of the grains. So the nitrogen parameters might be adjusted to nitride this part of the sample. Also, green regions here stands for the porous. This is because we use a special polymer to inject into the sample to fix the porous structure during the sample preparation process for TEM. Hysteresis loops of foil samples at each stage were collected, from raw foil to oxidized foil, reduced and nitride foils. First, we can see the saturation magnetization changes. As raw foil, it has high saturation magnetization since it's iron, and after oxidation, it decreases dramatically due to the iron oxide phases. After hydrogen reduction, the saturation magnetization recovered, but slightly lower than that of the raw foil because there's some oxidation at the surface of the foil. And then the nitrogen process was carried out after the reduction. We get the nitride foil, and we can see both saturation magnetization and coercivity are enhanced. The saturation magnetization here considerable, there might be some potential oxidation. So the saturation magnetization of alpha double prime and 16 nitrogen 2 should be even higher than this value. The enhanced coercivity is due to the large magnetic anisotropy of alpha double prime and 16 nitrogen 2. So first derivative of the nitride loops was shown in this figure, and we can see there are no kinks, indicating that the grains are magnetically exchange coupled well, and so some unreached region may have lower coercivity. Exchange coupled with the iron 16 nitrogen 2 grains can reduce coercivity. So that's why our coercivity of this foil sample is a little bit lower than that of the nanoparticle samples prepared by the similar low temperature nitriding process. From the hysteresis loops, we can see both saturation magnetization and the coercivity of the nitride foils are enhanced due to the formation of alpha double prime and 16 nitrogen 2. But the coercivity is relatively low compared to the nanoparticle samples. So we measured the delta M curve which can help us understand which kind of magnetic interaction between the grains in the foil sample. So as shown in this figure, for the positive value, the dominant is exchange interaction, and negative for dipolar interaction. We can see the exchange interaction is dominant in our sample. So as I discussed in the previous slide, there might be some unreached region in the sample. So one way to enhance coercivity is to reduce the unreached region to get a higher phase volume ratio of alpha double prime and 1692. Yeah. Another way is like figure out a way to reduce the exchange interactions between grains, like introduce some non-mag grain boundaries or some other methods. It's still ongoing for the research. So the temperature-dependent magnetic properties were investigated on the nitride foils, since as magnets it can be used at the world's temperature. Two commercially available neodymium boron permanent magnets were used as a comparison. One is N40, the other one is N52. These two values stand for the pH max of the magnets in McGaugh's Auster. For easier comparison, we normalized the coercivity and the remanence ratio of these three magnetic materials. And the temperature range we focused on is from 300K to 425K. Interestingly, we found that alpha double prime and 1692 foils has a positive temperature coefficient of coercivity instead of negative. This effect is due to the nitrogen atom Orlean effect in this temperature range in the nitride foils. For the neodymium iron boron permanent magnets, we can see they have a large negative temperature coefficient of coercivity, and the coercivity can decrease up to 80% with the temperature close to 420 Kelvin. And also, the neodymium iron boron permanent magnet shows a higher decrease rate of remanence ratio than that of alpha double prime and 1692 foils. So this makes the alpha double prime and 1692 a good candidate for applications at varying temperatures. But for the foil samples that we shown in previous slides, the coercivity is relatively low due to the unreached phase and the large exchange interaction of the grains. So more work needs to be done to enhance the coercivity and the pH max of the nitride foils. So this is the ongoing work we are working on. Here's a summary of my presentation. Alpha double prime and 1692 foils were successfully synthesized by low temperature nitriding for the first time. The pearl structure created by the combined oxidation and reduction process enhances the nitrogen diffusivity in an iron foil and can enhance the phase volume ratio of alpha double prime and 1692 in the nitride foils. Both saturation magnetization and coercivity are increased for the nitride foils due to the formation of alpha double prime and 1692 phase. A positive temperature coefficient of coercivity is obtained for the synthesized nitride foils, which is good for the applications at various temperatures. A magnet can also be made by stacking the nitride foils together. I would like to thank my advisor, Professor Jinming Wang, my colleagues, Professor Bin Ma, Dr. Yanfeng Jiang, Dr. Gunneng Guo, for the insightful discussions and constructive suggestions on the design of experiments and data analysis. Thanks to staffs in nanomagnetics for their help on sample preparation. Thanks to the staffs in characterization facility and the Institute of Rock Magnetism, University of Minnesota, for their help on sample characterizations. Thank you for your attention.